Okay guys, in this video lesson we're going to take it one step further for our voltaic cells and take a look at how we actually can calculate the amount of volts or amount of energy is available when we start to put these two different things together. Okay, to do that we need to talk about electromotive force. Okay, so the electromotive force is basically our way of determining the energy available for use. One thing we want to think about is waterfalls. Okay, of course, waterfalls. Now, a waterfall always falls in the same direction. Okay, you have a river, it comes to a cliff or a hole or something, and the water falls off it and lands. Now, small waterfalls, you can stand underneath them and play under them, and they're a lot of fun. Big waterfalls, you don't do that because as a water falls, it gains speed, and there's lots of mass there, and that would hurt and could possibly kill you if you stood underneath them and you had too much water falling on top of you. Okay, same thing happens for voltaic cells. We always have electrons flowing in one direction, or the spontaneous direction, okay? Which means they always leave the anode and they always flow to the cathode, okay? Now, when they leave the anode, they have a certain amount of potential energy there, okay? They have the potential to do something because they're electrons that have potential energy. As they flow through the circuit or the light bulb or the cell phone or whatever they're using to power, they use up some of that potential energy to power that device or to light up that light bulb. As a result, they return to the cathode at a lower potential energy. Okay, so they have a certain amount of potential in and a certain amount of potential out. As a result, there's a certain amount of energy transfer there. Okay, just like a waterfall, whereas the higher the waterfall, the more potential it has to hurt you if you sit underneath it. Okay, it has potential to fall off the cliff and land. So high waterfalls are kind of like things that have lots of energy, lots of potential energy. Kind of an analogy that we use. And that's kind of how the circuit works. Now, what we need to do is talk about what is this electromotive force and how do we actually calculate this potential, okay, this electronic potential inside of our cells. Okay, so to do that, we definitely want to have a couple of different things down definition-wise. All right, so first of all, potential difference between the anode and cathode, we call that the EMF, or the electromotive force, okay? We also call this the cell potential. You will probably hear me reference it as the cell potential more than anything else, okay? I don't use the term electromotive force a lot unless I'm in the world of physics. We call it our cell potential. We symbolize it as a capital E with the word cell as a subscript. That's saying that this is the cell potential, or this is the potential energy available for this cell, okay? Now, if you have a bunch of cells and you put them together, we call it maybe a battery of cells. So you put a cell linked to another cell, linked to another cell, linked to another cell. You actually can get a whole bunch of cell potentials put together, and we create a battery. Okay, so that's kind of what we're getting into is how do we make batteries. We do measure this in volts, okay? We're not going to dive deep into what a volt is in this unit. It's not really the scope of what we're trying to do here. It's just our unit that measures cell potential or measures this amount of force, okay? You have plenty of time next year in physics to dive deep into ohms and resistance and volts and amperages and all that kind of stuff. And that's more of their world, okay? So what we want to do is get some numbers to this thing, which means we need to know what the energy is or what the potential is anytime we do a chemical reaction. Now, recall when we do redox reactions, there's both an oxidation and there's a reduction, which means there's always two parts of our reaction. Now, we don't track both the oxidation and the reduction because they really are the same thing, just opposite direction. So what we do is we set up and we have tracked what we call standard reduction potentials, okay? Which means we're looking at what is the reduction half reaction for lots of different things. Now here's one chart, it's just one list I happen to have. You could look up others if you needed to. And let's take a look. So let's say, for example, fluorine. If you wanted to reduce fluorine from its gaseous state into fluorine ions, that reduction potential is a 0.287. So this is our biggest reduction potential that we have. Okay, it's a very big positive number, okay, to do this. Now, if you want to reduce sodium into sodium solid by giving it electrons, it's a negative reduction potential, okay? It should make sense that sodium, okay, is not as good at doing this as fluorine is. Think about it. Fluorine, okay, in terms of its charge, it's very electronegative, okay? So this idea of being highly electronegative, it makes sense that this was going to be a negative charge is going to happen. Sodium really doesn't want to be a solid. It wants to be in that positive state. So it makes sense that these should be on the opposite ends of our scale here, Okay, then we find iodine and oxygen and copper and nickel and iron and a whole bunch of different things in here as we do it. Okay, now we're going to use these half reactions and these numbers to solve for the overall cell potential. To do that, we need an equation. All right, so the cell potential at standard conditions is this equation. So we have cell potential, E with the cell behind it. Remember, our not symbol up here means standardized. So standard conditions, standard temperature, standard pressure, those kind of things, because temperature and pressure can affect this. More so temperature than pressure, but they both can affect it. You take the reduction potential at the cathode minus the reduction potential at the anode. Okay. Now notice it's reduction potential and reduction potential. Okay. We're basically taking them and subtracting them. Keep in mind though that at the cathode, okay, that's when the reduction really happens. At the anode, that's actually oxidation, if you recall back to our voltaic cell information. So what we're really saying here is you're taking the reduction of one thing and you're adding it to the oxidation of the other, okay? But oxidation is the opposite process, right? So you're going to take the reduction minus the reduction of the other one. So by putting a negative sign in here, we're actually able to talk about, even though this is oxidation, we're actually doing the opposite of oxidation, so it's reduction, okay? So that's kind of why the negative sign is in here, is it makes the math work out properly. All right, so let's do one, okay? So we have, what's the cell potential for the copper zinc voltaic cell? Okay, this is one we've done a lot. We've used copper zinc a lot. It's kind of a standard one that chemists use to learn this anyway. And we know that if you go back to our voltaic cell, zinc was the oxidation, okay? It was at the anode. Copper was the reduction. It was at the cathode, okay? If we look up our values for each of these, we can go back here and say, oh, well, here's copper. Copper's reduction potential is 0.34. Here's zinc's. Zinc's reduction potential is negative 0.76. It's also given to us here. So we're going to say, well, at the cathode minus what's at the anode. Okay? So we go down here, and our cathode was the copper with a 0.34. We're going to subtract away the anode, which is right here, the negative 0.76. And we take 0.34 minus a negative 0.76. And we're basically adding 0.76, and it comes out to be a nice clean 1.10 volts, okay? So what we have here is a cell potential of 1.10 volts. So if you hook up a single cell with zinc and copper system, you can generate 1.1 volts out of it. Now, if your device needs 2.2 volts, or your device needs 3.3 volts, or 4.4 volts, or what your device needs to power it, you might need to have more than one cell, okay? So you could take this cell and add it to another cell and get a 2-cell or a 3-cell system. Every time you have more than one cell, you get what we call a battery of cells, or we get a battery. So that's where the term battery comes from. It's actually the stacking of multiple cells together in series to generate more voltage. So we get a higher volts, okay? But each individual cell can hold 1.10 volts. Okay, let's do another one as practice, and let's check this one out, okay? I don't really care what we do. Let's kind of pick one out here. So let's go down here. Let's say we have iron metal reacting with aluminum metal, okay? So we have iron and aluminum, and now let's take a look at what's going to happen between those two things, all right? Now the question might become, well, how do I know which one's being oxidized? How do I know which one's being reduced, okay? So in terms of which one, is at the cathode and which one's at the anode, do we get to pick that? We say, oh, I'm going to make iron at the cathode, I'm going to make aluminum at the anode. We can't, okay? It's not our choice. It's really the choice of either iron and aluminum, who does what, okay? So if we go back, the oxidation one versus the reduction one, we take a look. Well, zinc was oxidized. It had a reduction potential of a negative 0.76. Copper was reduced. It's a positive 0.34. Which means if you put any two metals together and you look at them, you actually can determine which one will be oxidized, which will be reduced, just by looking at their cell potentials, okay? So the one that gets oxidized will be the lower value. The one that gets reduced will be the higher value, okay? So let's go back to our chart, okay? We go here, here's iron, it's a negative 0.44. Here's aluminum, it's a negative 0.166. Iron is the higher value, okay? The higher one, if we go back again, whoops, wrong direction here. There we go. The higher value is always the reduced one, okay? It's the one that will get reduced. So on this chart, the one that's higher gets reduced, okay? The one that is higher is going to be at the cathode. So we know, if we go to our little board here, so we know that the iron as a 2 plus is going to be at the cathode. So it will be reduced, okay? So it's going to gain electrons, okay? It has a better ability to gain electrons. The aluminum as a 3 plus will be at the anode, and it will be oxidized, okay? So we kind of know that's what's going on. It all comes back to a ranking system. Now, if you look, this ranking system as reduction half reactions should look familiar to you, but just flipped. Notice how lithium, sodium, aluminum, zinc are all at the bottom, okay? They're not very good at being reduced because they're good at being oxidized, okay? They're opposites. This is actually exactly opposite of our activity series, or for the most part, opposite of our activity series in terms of like which metal will do what to the other metal in terms of single displacement because of reduction. So that activity series is really built around these reduction potentials, all right? Now that we know these, we know the iron reduction potential is a negative 0.44. We know that the aluminum's reduction potential is a negative 1.66. And now we're ready to calculate, okay? So again, we want to make sure that we take our cathode minus our anode. So here's our cathode, and we have a negative 0.44, so we have a negative 0.44 minus our anode, so minus a negative 1.66. All right, so you take a negative 0.44 minus a 1.66, this becomes a positive, so we're basically taking 1.66 minus 0.44, and if we do that math, that becomes a 2, that becomes a 2, so it's 1.22, okay? So the cell potential standardized for this would be 1.22 volts. All right, there we go. Okay. So if I use iron and aluminum, I would get a voltage of 1.22 volts inside of one of my voltaic cells. All right. Again, things to keep in mind. One, how do you choose your cathode and anode? Okay. So the bigger number, okay, not the one furthest from zero, but the actually bigger number is the one that gets reduced. The smaller number, the most negative or whatever it happens to be, gets oxidized. So you know that oxidation is at the anode and the cathode is our reduction. So you know which way to put these things into our equation. All right? And we get a 1.22 volts for our second example on this one. One more little detail on this that I kind of glossed over or didn't even acknowledge actually is the fact that if we go back to our iron and our aluminum, you know, iron was a 2 plus and aluminum was a 3 plus. So in terms of the electron transfer there, it really isn't going to be a 1-to-1 ratio. Okay, so to get these to balance out, we're going to need to have like 3 irons and 2 aluminums to make this process work. Now, what's interesting about cell potentials is we don't care. Okay, in terms of voltage and how they work, it's an intrinsic property, which means we don't care how much of it is there. You can have a 2 to 3, a 1 to 1, 8 to 5, whatever the ratio is, we do not care. It does not affect our results. Okay, so it's kind of like density, where we don't care if we have a lot of copper or a little bit of copper. Its density is always the same. All right, same thing here. We don't care if we have a lot of aluminum or a little iron, a lot of iron. It doesn't matter. The cell potential will always be the same. Okay, so if you're wondering about, wait a minute, you know, one was a +2, one was a +3, does that affect things? It actually doesn't, which is kind of nice because it makes our math even easier. Okay, all right, guys, that is it. Our next thing that we're going to run into is batteries and how batteries work, and we'll go and dive into actually several different types of batteries to kind of give you some insight on them. Thank you.